Great, thank you for coming. I'm very happy to have the Weinan talk in the Math and Data Zurich remote seminar. This is an experiment that we're doing to try to run seminars where we can all attend, even though a lot of us can't come out of our houses. And yeah, I'm particularly excited to have Weinan not only speak in our seminar but speak about this particular talk, because a lot of my colleagues at NYU heard it, and everyone told me wonders about it. They called it thought-provoking, quite a few of them, so I'm quite excited to hear it. Weinan is, of course, needs no introductions. Has a distinguished career, has worked in all sorts of fields in applied math, has done a lot of physical applied math, differential equations, modeling, and so on. Has recently taken an interest in machine learning. As far as I understand, both from the perspective of having machine learning help in physical applied math and modeling, and now this talk is about the help going the other way. So I'm particularly excited to see how insight from modeling and physical applied math can help in machine learning. I should say that my favorite memory of Weinan is when I was a first-year PhD student. Weinan was actually the director of graduate studies at PACM in Princeton. And in Princeton, in math, there was no course requirements, and I wanted to ask Weinan as DGS which courses I should take, what should I do, what should I look into, and so on. And I remember that, I don't remember exactly the words, but he said something like this: you should figure it out, it's completely up to you, you should decide. In hindsight, this was maybe one of the best advice I ever gotten. It really made me take a step back and think about what I wanted to do. So I very much appreciate that advice from, I don't know if you remember it, from around 10 years ago. And yeah, please, I guess you're not here to listen to me, so please welcome Weinan. We don't have the normal clapping, but consider it a virtual clapping. And if there's any questions, please, in the beginning, I'll allow interruptions. If there's too much, I'll stop them, and just write on the chat. I can also ask questions. All right, thank you so much.
Well, thank you, Alfonso. I'm still the DGS at Princeton here. So thank you very much for arranging this talk. This is my first experience. I hope this thing works out. We'll see. What I want to do is to present a sort of a viewpoint of machine learning from the as a classical numerical analyst. So by which I mean people who worked on approximation of functions, solving PDEs, linear algebra, optimization problem, worrying about convergence rates, designing principles for numerical schemes, models, etc. But with a new twist, which is that these problems that we have in machine learning are problems in very high dimension. As a matter of fact, the slides is on my my homepage. Okay, so here's a rough outline. I have 60 slides, so I might not be able to finish. But let me just say section 5 is about deep neural network models. So essentially, I'll talk about the viewpoint using random feature models and two-layer neural networks as an example. And then section 5 would be the extension to deep neural networks. I might have to rush through those. Okay, so let's start with the basic example, the supervised learning. So we are given a set of data, which is S, where the Y's are function values. So these are, F star is our target function. We're given the function value at some particular data point xj, and our task is to learn F star, which meaning approximate F star. So this problem is clearly a approximation problem. It's approximating functions. And then we have a finite piece of labeled data. So Y is called label. If the values of Y is discrete, this is called a classification problem. If the values of Y is continuous, F star is continuous, and we call it a regression problem. And I'm going to restrict ourselves to the case where the domain of interest is unit Q and neglect measurement noise. So there's no noise in the values of Y. And noise is actually not that important in this discussion here. Okay, and notation-wise, mu is the distribution of the data X. In practice, you would divide S into two sets. One is a training set for which you train your model, you learn F star. The other is a testing set for which you use to test how good your approximate F star is. This is the classical example, classifying images, C410 image data set where there are let's see, 10 categories of images. And the dimension here is 32 by 32. That's the number of pixels, and times 3 color dimensions of color space. So that's, I can't see this, 3,000 spaces, 3,000 dimensions. And the function value is from 0, 1 to 10 function values, discrete function values, the classification problem. As an example of a regression problem, how come it doesn't move anymore? Okay, so it looks like, so this is an example of a regression problem. It's about learning the interaction potential between lots of atoms. So if you want to do molecular dynamics, often done in chemistry, material science, you need to know how the atoms interact with each other. And that's the potential energy function. And that function is a function of many, many variables. So this is an example where we've used deep learning-based technology to fit, to try to come up with models for this interaction potential using data from quantum mechanics. You can see there are different kinds of systems discussed here. The small molecules, they're very high entropy alloy, they're oxidized, they're big molecules, also all the stuff. So uniformly across different kinds of materials and molecular systems, you can see the accuracy is pretty well. By the way, the horizontal axis is the quantum mechanics result, and the vertical axis is the prediction from the machine learning model. If the data lies on the diagonal, that means no error. So deviation from the diagonal, the scatter from the diagonal is the size of the error. Basically, one can conclude that the error is comparable to the error in the original quantum mechanics model. Here is the DFT, density functional theory. So other examples, so I put on this slide to make the point that when people think about machine learning, they often think about applications to artificial intelligence. So computer vision, natural language processing, videos and stuff like that. So in recent years, actually, applications to science and to computational science has been a major driving force, and particularly molecular dynamics, quantum mechanics, etc. And also to high dimensional PDEs. So that's another area that I think would be we'll see a lot of growth. Studying high dimensional PDEs, we're able to come up with algorithms that can solve PDEs in hundreds, maybe even thousands of dimensions, something that one could not have imagined before. So and with that, there's also an interesting question of how do we think about mathematically think about high dimensional PDEs. The fact that we can compute solutions to such PDEs means that the solutions could not be too complicated. So how do we quantify that? That's another issue that I think will be very exciting in the near future. And also control problems. Control problems has been, real application of control problems has been an issue because of its dimensionality. So now there are algorithms that can, solve control problems in not in millions of dimensions, but at least thousands of dimensions. So the standard procedure for supervised learning, there are 3 steps. The first step, so we're going to focus on a regression problem. The first step is to choose the hypothesis space. That's just a set of trial functions that we're going to use to fit our function, to approximate a target function. So we call that HM, where M is roughly the dimensionality of that hypothesis space, number of degrees of freedom. For example, classically, we use piecewise polynomials, wavelets, and stuff like that. So nowadays, in the context of machine learning, we use neural network models. The second step is to choose the loss function. So that's a function we're going to minimize in order to fit, to find the approximation to F star. So standard loss function is this empirical risk. So we just minimize the error on the data set xj. Sometimes we add a regularization term. The third step is to actually minimize this loss function. So choose an optimization algorithm and choose the hyperparameters that goes with the optimization algorithm. So the overwhelmingly most popular optimization algorithm in machine learning is stochastic gradient descent. So I'm not going to speak very much about stochastic gradient descent. I'll talk instead more about gradient descent. So these are the 3 major steps. Now, keep in mind, when we select these particular components in each one of these steps, what we really want to achieve is to minimize what is called the population risk, and is also known as the generalization error, namely the error that we're making over the whole data. The important parameters here are m, this m here, n, and then t, which is the number of steps that we're going to use in the optimization algorithm. And as I said, there's also dimensionality d. As I said, the d is typically very high. Now let's take a first look at the error. So f star is our target function. F hat is the output of the machine learning model, whatever the model is. And let's denote by fm the best approximation in the hypothesis space. So we can decompose this error into two parts. The first is f star and fm. So that we call approximation error, because that depends only on the hypothesis space. That means, if you do the best in your hypothesis space, how big is the error? And the second part we call estimation error. That's the additional error caused by the fact that we only know a finite piece of amount of data, so we have to make a compromise. So we're making an additional error. That's called the estimation error. So let me look at these two errors separately. First, let's look at the approximation error. So as I said, that depends on how we choose the hypothesis space. If we choose, classically, we choose polynomials, piecewise polynomials, splines, and all kind of stuff. But for all these, essentially all these different choices, the error estimates we would get looks like the following. Remember, m is the number of parameters. So here we're looking at the L2 error. This is the sublevel norm, doesn't really matter. But what's important is this thing, this factor here. So this factor has a component, the alpha, 1 or 2, 3, that depends on particular approximation scheme. But the important factor is the D here, the dimensionality. That's the signature for curse over dimensionality. So that means that if you want to make this term to be 0.1, then m has to be 10 to the d, if alpha equal to 1. And in machine learning, it's not such a surprise to look at d equal to a million. So 10 to the million is a huge number. So this is the kind of a problem, classical problem, that has been blocking our progress in many different areas. Okay, so we have to think about high dimension. So now in numerical analysis, there's only one problem that I'm aware in which high dimension, we have studied a high dimensional version of the problem rather thoroughly. That's the Monte Carlo integration. So we're studying, we are interested in computing this integral over the unit cube. And typical, if you do trapezoidal rule or Simpson's rule, you would have curse of dimensionality. But you can do Monte Carlo. Namely, you pick an IID samples uniformly distributed in the unit cube, and you approximate this integral by this empirical sum expectation. And then this is the identity. Then the error goes down like the variance of this function over n. So two important things. One is that the rate is like 1 over square root of n. There's no 1 over d here. So that's a good news. The second piece of information is that the constant, the error constant, is the variance. This variance in practice can be very, very large. If you do a statistical mechanics problems, this can be a very big number. So therefore, variance reduction is very important. One could say that Monte Carlo integration is about variance reduction. So what do we learn from this? Well, we want practically, we want to do the same thing, but in the context of approximating functions. So one motivation from this is that we might have to express functions as expectations. If we can express functions as expectations, then computing the function, approximating the function, is like approximating a quadrature. Maybe we would have the same story. So that's one thing we can learn from this little example. So that's about approximation error. Basically, we have this problem of cursive dimensionality, and we have inspirations coming from Monte Carlo integration. Let me just say, just comment that in Monte Carlo integration, it's routinely, in statistical physics, one routinely computes integrals of millions of dimensions. And if you think about it, that's also amazing. So we basically want to do the similar things, but for more complicated tasks, such as approximating functions, solving PDEs, modeling dynamical systems like that. Okay, let's look at the estimation error. So this is the classical Runge phenomena in numerical analysis. It's about interpolating functions on an equally spaced grid. So I didn't mark the grid, so these are the grid points where the curves intersect each other. So what happens is that here on the data set, namely the grid points, we have perfect match. The error is 0. But away from the data set, you have huge error, especially at the boundary. This is the classical Runge phenomena. And similar things might happen. That would be bad news. That means our empirical risk is 0, but our population risk can be very large. So this is something that we don't like. So how do we estimate the difference between the two? So this is the notion of a generalization gap. Namely, F star, if you recall, is the output of the machine learning model from minimizing the loss function, here the empirical risk. And the value of the F star, the population risk evaluated at F hat. And the difference between these two is called the generalization gap. So we want this gap to be small. Therefore, if this is small, then this is small. So we want this gap to be small. If you look at it, well, this is the definition of R hat, the empirical risk. This is the definition of population risk. You might be tempted to say, well, this just looks like a Monte Carlo discretization of this guy. Therefore, you would expect that the error is like 1/√n, which I just showed you. This argument is wrong because the argument I presented before rely on the fact that everything is independent. Here, our F hat comes out of the minimization of this empirical risk, which is intimately related to data. So everything is very much correlated. So therefore, this error may in general not be 1/√n. As a matter of fact, this is one of the hardest problems in machine learning. So how do we deal with this? Well, let's use the trivial bound. Namely, F hat is in the hypothesis space. So this gap cannot be bigger than the supremum of this gap. And this quantity, so now we just have to estimate this quantity. Now, this quantity depends on how we choose the hypothesis space. For example, if we choose the hypothesis space to be a unit ball in the Lipschitz space of Lipschitz functions, so functions for which the Lipschitz constant is bigger than less than 1, then this quantity scales like 1/n to the 1/d. By the way, this is the definition of Wasserstein metric, the Wasserstein distance, related to Wasserstein distance. So you have a 1/d here. So this is the cursive dimensionality associated with the data set, the sample size. In contrast, so Lipschitz, unit ball in Lipschitz space is a bad space. In contrast, if we choose unit ball in what do we call barren space, which we will define later, then you would have 1/√n. So this is what the kind of estimates you would like to have, because this is comparable to Monte Carlo. The spaces that satisfy this properties are roughly called Donsker spaces, named after Donsker, who came up with the invariance principle. Well, to control this kind of a quantity, I've changed to H instead of F. No, actually it's H here. To control this kind of a quantity, a classical notion is the Rademacher complexity, which is defined here. Roughly, this estimates how the functions in hypothesis space can fit random noise. So Kasai is a random variable, IID random variable, taking value ±1 with equal probability. So how well your hypothesis space functions would fit the random data, random noise. If your hypothesis space can fit random noise extremely well, that's a very complicated hypothesis space. That means your space is very complicated. That means the error could be very large. The reason we're interested in this quantity, the Rademacher complexity, is that it bounds from above and below the quantity we're interested in, up to some logarithmic terms, which comes from applications of concentration inequality. So I'm going to neglect all terms, I'm going to forget about, I write them down, but I'm not going to mention too much about these kinds of terms, which comes as a consequence of concentration inequality. So the kind of theorems you'll see is always like this, with high probability that we have error like that, up to some logarithmic terms in delta. So up to such terms, this quantity we're interested in is bounded from above and below by Rademacher complexity. So everything reduced to estimates of Rademacher complexity. Now, Rademacher complexity is not the only way to deal with generalization gap. There are other ways, but for this talk, I focus on Rademacher complexity. Okay, so summarize, we can divide all machine learning models in two kinds. One is the models that do suffer from cursive dimensionality, either in terms of approximation error or in terms of estimation error, the sample size that's required. So here's the number of parameters that's required. Here's the sample size that's required. Classical approximation schemes like piecewise polynomials, wavelets, and all that stuff are in this class. So they don't work for high dimensional situations. The second class, which are the class we're interested in, are the models that do not suffer from the cursive dimensionality. So we would have estimates like this, 1 over m times 1 over square root of n. So here we have 1 over m instead of 1 over square root of m. It's because that our error is squared. If you remember, the definition of generalization error has a square in it. Okay, so I'll discuss models in this class. But let me mention there's another issue of cursive dimensionality that comes from the optimization algorithm. So when you might have a model that has good solutions, solutions that approximate without cursive dimensionality, but finding them could be hard. So that's another potential issue, but for which at the moment we don't have a complete understanding, or even reasonable understanding. So I'm not going to speak very much about it, but that's a very important issue. Okay, so now let me also remark that that in order to achieve bounds like this, there is a tricky balance between the approximation and the estimation error, because for the approximation error to be small, you want large hypothesis space, because then you can approximate your target function well. For the estimation error to be small, you want small hypothesis space, because you don't want your hypothesis space to be too complicated. If it's too complicated, then you have large generalization gap. That's bad for this term, like the Lipschitz, unit Boy Lipschitz space. That would be bad. Okay, so that's sort of an introduction, which took too long, I assume. So let me now go on to presenting. So how should we think about developing models in this class? The first thing is think about how do we represent functions. Okay, typically, this is a very classical example of representing functions, namely Fourier transform. And then we have the discrete Fourier transform, where omega j is grid points on a regular grid and a uniform grid. That's the classical discrete Fourier transform. Then I already mentioned that you have the cursive dimensionality in this approximation. A new approach is to replace this d omega by a probability distribution, pi d omega. Then in order to approximate this, it's natural to do Monte Carlo. Namely, we take an RID sample of pi and then approximate this by this. And then, as I said, the error is like 1 over square root of m. Then there's no cursive dimensionality. This is a very, very simple idea, but very important. So we can extend this a little bit. Instead of just using exponentials, we can use other activation functions. For example, we can take ReLU, this kind of an activation function, which is most popular now in machine learning. So we get something like this. Okay, so let me now say that there should be like a bias. There's a constant term here, but I'm going to neglect all that. So, typical machine learning that this should be x tilde, namely there's a constant term, but I'm going to just adopt the standard abuse of notation. Now, we can do this, adopt this form, or we can also lump the A into the space of random variables and define a bigger probability distribution and write this as in equivalent form. So now, as I said, if you can approximate by discretization. So now there are two situations. One is we view pi as being fixed. So we are given pi, and then we just discretize A. So we evaluate, so we can approximate, in that case, we approximate pi by some empirical distribution, and AJ would just be the value of that function. We just approximate the value of that function at these points, and then we get this kind of approximation. This is called the random feature model. In this case, the parameters are just the coefficients here. Or we can view pi to be part of the parameters. We allow both pi and A to change. Okay, so in that case, the parameters would be A and omega, W, and this is the two-layer neural network model. So what I'm saying is that discretizing this continuous approximation leads naturally to random feature and two-layer neural network models. For two-layer neural network models, the parameters are both the A's and the W's. Okay, so now let me go on to presenting some sort of approximation theory, error estimates. So I've started with the random feature model. As I just said, the random feature model, it looks like this. So here I've generalized slightly the notation. Instead of just sigma here, I put in 5, which is a sort of a more general dependence on the parameters and the variable x. So this is the hypothesis space for the random feature model. The parameters are the coefficients. Omega wj is a fixed IID samples of the probability distribution pi. We can define a norm. Okay, we're going to look at functions that has the continuous form. This is very much an extension of what I wrote here. Well, maybe here. So just replace sigma by 5. Okay, so that's this. And associated with this kind of functions, we define a norm. Now this norm is an actual norm. In particular, when p equal to 2, then this norm is nothing but the norm associated with the reproducing kernel Hilbert space with a kernel defined by this activation function and the probability distribution pi. And we have, this is just the LP generalization of this norm in reproducing kernel Hilbert space. Okay, so what I'm saying here is that we have this model, approximation scheme, the random feature model, and associated with that model, there is a very natural function space with a function norm. Why do I claim that that's very natural? Because for this space of functions with this norm, there is a inverse and a direct approximation theorem. So this is just like classical approximation theory. If you recall classical approximation theory, for each approximation scheme, like piecewise linear polynomial approximation, we have a natural space, namely the Sobolev space, a Bessel space associated with that scheme, and for which there's a direct and approximation theorem, which basically says that if your function is in that space, then it can be approximated with an optimal accuracy, here 1/m, with the norm as the coefficient. And if your function can be approximated by functions in that space, then your target function, if your function can be approximated by the approximation scheme, so here the random feature model, then your function, the target function, has to be in the function space. And it may seem convoluted, but it's a very simple statement. Namely, saying that approximately speaking, so this is not optimal. There's a lot of I's and T's to be dotted and dashed. But roughly speaking, it says that this class of functions are naturally associated with this particular model in the sense that these functions can be approximated by this by the random feature model with optimal accuracy. And conversely, if a function can be approximated if a function can be approximated by random feature model with some uniform bounds, note that there's a uniform bound here, with some uniform bounds, then that target function has to be in my space. Okay, so this is the approximation theory for random feature model. Now with that, we can consider a regularized model. So with this particular regularization where the norm is defined previously, and then one can show that minimizers of this regularized model has almost Monte Carlo-like generalization error. So this is the generalization error bounded by 1 over m, 1 over square root of n. By the way, these terms can be removed if you want. I mean, this is just for simplicity. So basically what I'm emphasizing is that we have 1 over m, 1 over square root of n kind of estimates with coefficients defined by the norms that I just defined. Okay, so why do we do this? So here we're considering a regularized model. The virtue of these kinds of results is to show that good solutions do exist. There are nice solutions with good approximation error. Okay? And if you compare these kind of results with classical, more standard machine learning estimates, machine learning estimates is about generalization gap. And there, here we call a priori estimates. That's another thing I should talk about. Here we go a priori estimates because these are like a priori estimates in finite elements. Because on the right-hand side, we have the norms of the target function, not the norms of the solution, not like the theta hat of the f hat. So in classical machine learning, the estimates are typically the other way around. They are what we call a posteriori error estimates. Namely, they have generalization gap, not the generalization error, but generalization gap bounded by something, and with here replaced by the norms of the solution, the optimal parameters, the output of the machine learning model. Okay, so that's a typical classical statement. The problem with that is that these, the norms of these machine learning models, the solutions output of machine learning models, it's hard to control them. They can go to huge numbers, 10 to the 40, huge numbers. Now the problem with this kind of estimates, the priori estimates, is that we don't know these guys. We don't know how big these norms are because that depends on target function, which we don't know. In classical numerical analysis, we don't just have finite element estimates, we also have PDE theory, which gives us control of these norms in terms of the norms of the data. So that part is missing here in machine learning. But at this moment, let's just say that the virtue of these theorems is to tell us at least we have Monte Carlo-like estimates for these class of models. Now, the similar things can be done for two-layer neural network models. In this case, the replacement of the reproducing kernel Hilbert space is barren space. So basically, we want to carry out the same scheme. We're going to consider two-layer neural networks. Okay, so these are the two-layer neural networks. This is going to be our approximation scheme. We want to find the right function space for that approximation scheme. So for it means that we want to define the right norm, and that norm turned to be this guy. So in this case, we have to consider functions that can be represented by this in this form. Okay. Now you want to ask, well, what kind of functions can be represented by this form? This looks quite abstract. You want to ask what kind of functions can be represented by this form. So so this is actually a subtle issue. It might take 5 minutes to explain this. So if people are interested, I can come back to this at the end. But at this moment, let's just skip this part. So let's just abstractly consider functions that can be represented by this form. As I'm going to argue later, that we have to consider functions in this form because these are the exact functions that can be approximated by two-layer neural networks. Associated with functions of this form, we define a norm. Okay, since this representation here, in this representation, the probability distribution that gives rise to f is not unique. So here we minimize over all the probability distributions that gives rise to F. Okay. So these class of functions we call barren functions, because Barron has worked on similar things since early 90s. Really deserves the credit. Now, barren functions are related to reproducing kernel hero spaces. For example, as I said earlier, so in both cases, we consider functions of this form. As a matter of fact, we consider functions of this form in both cases. The difference being that for reproducing kernel hero space, this pi is fixed. For barren function, pi is associated with F star, is adapted to F star. So in some sense, we can write barren functions as the union of all reproducing kernel hero spaces with kernel defined by all different kinds of pi. Okay. So typically in reproducing kernel hero space, you fix pi. And that's also what happens in random feature models, you fix pi. In barren, pi is adapted to your data or your target function. So in some sense, two-layer neural networks is like an adaptive version of random feature models for which the kernel is adapted to the data. Okay, as I've already alluded to, that with barren space, one can prove the direct and the inverse approximation theorems for two-layer neural networks. This is the direct approximation theorem. You can see the norm here, F in the barren norm, and this is the inverse approximation theorem, which basically asserts that if any function can be approximated by two-layer neural networks with some uniform bounds, then that function has to be in the barren space, has to have this kind of a representation, and the norm, barren norm, has to be finite. So let me just mention that the proof of these kinds of theorem, this is basically from Monte Carlo. This is some sort of a compactness theorem. A nice thing about the barren space is that you can show that its Radamel complexity, remember the Radamel complexity, has the optimal 1 over square root of n scaling. So this was first established by Bach. Okay, with that, then everything put together, in the same way, we regularize by this barren norm. This is the discrete barren norm, discrete analog of barren norm for the two-layer neural network. If we regularize by the discrete analog of the barren norm, then the minimizers of this regularized model satisfies this Monte Carlo-like error estimates with the barren norm as the coefficient. Since barren norm is smaller than random feature model, the reproducing kernel Hilbert space norm, so these, compared with, you might think of going from random feature model to two-layer neural network model as a variance reduction step. Okay, so now let me say something about the optimization problem. So first of all, we're going to optimize this by gradient flow. So how do we define the gradient flow? So this is some sort of motivation from statistical mechanics. So here, remember, this is the representational function, and then the population risk. Let's first look at the continuous version first. So we have this population risk, which we wanted to minimize, and this is like our free energy, and we want to minimize the free energy using gradient flow. In statistical physics, 1977, there's a very influential paper written by Harprin and Holmberg. Harprin is a Nobel Prize winner. Holmberg was almost a Nobel Prize. He proved the basic theorem for density functional theory. His collaborator, Walter Kuhn, got the Nobel Prize. Anyway, so very influential paper in which they define what is called Model A and Model B and all kinds of other models, gradient flows. Basically, if you look at the parameters here, A and pi, these parameters are different kind of parameters. Pi is the probability distribution. So it has to stay non-negative. In particular, the total integral has to be 1. So that kind of parameters are called conservative parameters. A, in contrast, is a non-conserved order parameter. By the way, they call order parameter. So for non-conserved order parameter, we just do straightforward gradient flow. And the Allen-Kahn equation is produced that way. For conserved order parameter, we do what is called model B gradient flow. Kahn-Hilliard equation, for PDE people would know, is produced that way. So to do model B gradient flow is generally the following way. So in the physics terminology, the variational derivative is the chemical potential. And from the chemical potential, we get the velocity. Actually, there is a, we get the velocity. The gradient is the velocity. And then from that, we get the current. And the gradient flow is just the density continuity equation. This also happened to be the gradient flow with, of the original free energy with respect to Wasserstein metric. But in the physics mind, this is the gradient flow for some densities that comes from chemical potential. Okay, so we're going to follow the same strategy. Now, but let's look at some more details. For example, suppose we're looking at a feature-based model, namely we only optimize over A. So pi is fixed, is given and fixed. So then this Allen-Kahn equation, this guy, become this form, is this. If you look at it, this is just a linear integral equation with a kernel defined in the following way, and that's positive definite, with a symmetric positive definite kernel. So this is a rather simple PDE, actually integral equation. And in particular, the energy, it has the right convexity properties. And we can define this Lyapunov function, and we can show that this is indeed a Lyapunov function. And from this Lyapunov function, one can show that the L2 norm is bounded, and from the boundedness of the L2 norm, we can control the population risk. 1 over T decay. Notice that there's no deep dimensional dependence. In the case of conservative gradient flow, namely, let's look at the parameter is regarded as a probability distribution. Then the gradient flow looks like this. As I said, that this is the Wasserstein, this is the gradient flow in the Wasserstein metric. And this is the same equation, the mean field equation, derived by several groups of people by studying the continuum limit of 2-layer neural networks. So here, the starting point is the 2-layer neural network, finite size 2-layer neural network, as the size of the neural network goes to infinity. And you regard these neurons as being particles, and you invoke the analogy with interacting particle systems. And in the continuum limit, the mean field limit, it's called mean field because these particles interact with the target function, with the function. They don't interact directly with each other. So in that limit, you get this continuum equation, the Vlasov-McKean equation. So semi equation. Now, even though our original functional, the free energy is a nice convex, functional, for this kind of a gradient flow on a Wasserstein metric, convexity is not enough. You require, at least currently, the theory requires displacement convexity. If the functional is displacement convex, then there is an analog of this additional functional, everything would follow. But unfortunately, our functional is not displacement convex. So for this reason, or any other or other reasons, that right now at this moment, there theoretical results for this flow is lacking, and this I think is a very interesting and important problem for machine learning. So far we just discussed gradient flow in a continuous framework. Of course, that's not good enough. We need to discretize in order to get some real algorithm. In order to discretize, we have several things to discretize. We discretize the population risk into empirical risk using data, obviously. And then we discretize the flow. this flow or this flow. But these are just like PDEs or integral equations. When we describe PDEs and integral equations, we have many ways to do these. There's the classical numerical analysis. For example, we can do spectral method. And this is very effective in low dimensions. But in high dimensions, if you think about cursive dimensionality, then, I already alluded to Monte Carlo is the way to go. And the dynamic version of Monte Carlo is the particle method. So we would prefer particle method or smooth particle method. If you know vortex method in fluid mechanics, the analog of vortex blob method. So, okay, so what I'm going to say next is that if we do this, if we use particle method to discretize these PDEs, okay, I call them PDEs, they're not really PDEs, but I call them PDEs. Anyway, they're, I'm going to say that in the next few slides that if you use particle method to discretize this continuum PD-like models, you will recover exactly the gradient flow for the random feature model and neural network model. Okay, so here we go. These are details. So this is the PDE for the feature-based model. Here we go. This is the integral equation. So how do we discretize using particle method? Well, we replace the probability distribution by some empirical probability distribution, where omega j is some fixed samples of pi, and then the A's are the ones we want to compute. For those A's, the particle method would give rise to this set of ODEs. And it's easier to check that this is nothing but the continuous version of the gradient flow for the random feature model. Okay, so now let me say something about what happens with the random feature model in the gradient flow of this random feature model. We're going to study three regimes. The over-parameterized regime, why does it look like this? The over-parameterized regime, in which there are many, many more parameters than the size of the data. The under-parameterized regime, the opposite, and then the resonant regime, for which these two, M and N are almost the same. Okay, so let's first look at the over-parameterized regime. Let's take the extreme case when M is infinite. So then our particle method or gradient flow becomes continuous because M is infinite. And again, we have the additional Lyapunov function from which we can conclude that the generalization error is bounded as, this 1/t bounds still holds. The 1/t is like the analog of Monte Carlo in this case. And similar story for the under-parameterized regime. So since time is limited, I'm going to skip this. Basically, the convexity estimates isn't enough to get these 1/t kind of estimates. We had a 1/m already. The interesting regime is the resonant regime when M is roughly equal to N. Something interesting happens, which was called, there's a phenomenon called double descent. So if you look at, this is the random feature model applied to the simple MNIST data set. This is the MNIST data set, where the size of the sample is 500. M is the number of features. You can see this is the test error. You can see that test error this has a peak at M equal to N. At the time, if you look at the eigenvalue, the smallest eigenvalue of this matrix, the Gram matrix, this matrix here, the smallest eigenvalue becomes very small at the same place. So this is a resonance phenomenon where it's caused by small eigenvalues. So this is bad news because it says that particular regime, the generalization error can be very large. As a matter of fact, it can be really large, as I'm going to show. But there's another side of the story, namely, if you look at the dynamics, if you look at the gradient descent dynamics. So here is the gradient descent, here is the test error, the behavioral test error, as the gradient dynamics proceeds. You can see it suddenly becomes very large at the end. That's very large in test error. But in the middle, there's a big regime for which the test error is small. As a matter of fact, if you stop your gradient descent iteration at small time steps, for example, 10 to the 4, and then the test error as a function of the number of features is not so bad. But if you're really, really patient, suppose you're an extremely patient person, and you stop it at 10 to the 12, you go on to the 10 to the 12, then you would have very bad result, much worse result because of this resonance. Okay, why is it so? This is because, as I said earlier, that this bad thing behavior is caused by small eigenvalues. Here, the small eigenvalues is very small. As a matter, goes to 0 as m goes to infinity. By the way, there's some sort of random matrix story that's behind this, but I'm not going to talk about it. But small eigenvalues also takes a very, very long time to develop because you have e to the minus lambda t in the dynamics. So it takes a very, very long time to develop. As a matter of fact, one can turn this into a theorem. So this is a special case when we look at, okay, this is just to illustrate, we choose the eigenfunctions, the first eigenfunction of the kernel operator to be the target function. And these are the singular values of this matrix. Never mind the details. The important thing of this theorem is stated in the figure, actually. So if you look at the training error, it has 3, the blue curve is the training error. It has 3 regimes. The first regime is, dominated by the first term, namely your error in the large, in the component corresponds to the large eigenfunctions, large top eigenfunctions, exponentially decays. And the third regime is when the noise that's sort of in the numerical noise in the high eigenfunctions for the small eigenvalues becomes dominant. So then you get really bad test error. And in the middle, there are several decades, here like 3 decades, 4 decades in which the test error is small. And this is a general feature as n becomes big. So on one hand, if you just look at the optimal solution, the so-called optimal solution, the solution that minimize the empirical risk, the test error is bad. The generalization error is bad. On the other hand, gradient descent saves you. You really have to be extremely patient in order to see that problem. And this, I think, is one of the reasons why machine learning models seem to work out. Okay, now let's turn into 2-layer neural networks, which also means that conservative dynamics. Again, if you discretize using particle method, you recover the gradient descent dynamics for the random for the 2-layer neural network. As a matter of fact, notice that the one thing that's interesting is that this PDE, which should happen for the continuum limit or the continuous limit of the for the interaction particles, actually also holds for any set of finite neurons. And in that case, this PDE just reduced to this ODE set of ODE, which is nothing but the gradient descent dynamics for the 2-layer neural network. And for that same reason, this PDE has all the complexity of the finite of the gradient descent dynamics for finite neuron problem. So it's not that clear in what sense this PDE sort of would help us, but it does. It's just much more subtle. So there are, very few theoretical results so far. Let me just say one thing. So I said if you discretize this way, then you recover. If you choose discretize this way, and in particular choose initial conditions this way, then you get this ODEs, which are exactly the same as gradient descent dynamics for 2-layer neural networks. But in practice, then hopefully everything will be nice because we're so following the PDE. But in practice, that's not what people do. People actually use different set of different scaling and different initialization but things still don't seem to go bad. So there's something called implicit realization that we're hoping to look to identify. So I would say there's very little understanding of this so far. We're in the process of, we've done very systematic and rather comprehensive phenomenological study of this. We're in the process of writing a paper on this issue. In particular, we have we think we've identified some mechanism for implicit realization, but I won't be able to talk about today. Maybe in a month, we'll be able to talk about this. But that's an important issue. So I sort of said that if you look at everything from a continuous viewpoint and then discretize, then you can recover all the current machine learning models. But that's not what people do. In principle, that's a very good idea, but that's not what people do. So understanding what people do and why that works is another issue. So here is an example. So anyway, so I'm going to just go very quickly. Oh, my time is running out. To deep neural networks. So basically, I want to say that similar story holds for deep neural networks, in which case we have to study flow-based representation. Alfonso, when should I stop?
You can take 5 more minutes, it's okay.
Okay. So here, there's another viewpoint to look at machine learning, namely look at it from a dynamical system viewpoint. If we study these ODEs, the flow map for this ODE is a nonlinear map. And if you choose sufficient number of class of Gs, you would get a lot of nonlinear maps. And then you contract these nonlinear maps by a vector, you get lots of functions. So that's another way to look at machine learning. So to cook up machine learning models, define hypothesis space. And this turned out to be the limit for residual neural networks. So if you take these are the residual neural networks, which is the neural network, deep neural network of choice if you want to build really, really deep, hundreds and thousands of layers of neural networks. And these guys are intimately related to the ODEs I was talking about with this particular choice over the right-hand side. So here, I talk about this, but I didn't say what G should be. And the answer is that the G should be these guys. Notice that these guys are nothing but the kind of representation I was talking about before. So here, basically, I'm saying that you should use the integral representation as the right-hand side of my flow. Then this flow-based representation is also a nice continuum model. And then you can build the same thing. You can write down the continuous model, the free energy, the flow, all that stuff. And if you discretize this, you would get the residual neural network. And I'm going to just skip this. So there's also approximation theory. There's the analogous of Barron space, which in this case we call compositional function space. I'm going to skip this because this is actually, the spirit is very much like the Barron space, but if this is the first time you're looking at it, it's very convoluted. Anyway, and you have the optimal direct and inverse approximation theorems, and the Rademacher complexity, and the analogous a priori estimates if you regularize. So this theorem shows that there are good solutions. And similarly, if you look at the flow, in this case, we have to define Weierstein flow in the extended space because now we have a one parameter family of probability distributions, not just one tau, not just one row, but a one parameter family of rows. So we have to define an extended Weierstein metric, and you can write down the continuum flow in that extended Weierstein metric, and that's given by this. For people who know about control theory, you will recognize this is sort of like the forward-backward equation control theory. And then if you discretize this kind of a flow using particle method, you would recover the GD dynamics, gradient descent dynamics for deep neural networks, for deep residual neural networks. Okay, so let me summarize. So I basically presented a viewpoint, sort of a numerical analysis of viewpoint. at this point, very highly unpopular, but I think this is, personally, I think this is the right way to think about it. And the right approach is to start with a continuous formulation of a problem. And to do that, we first have to think about how to represent functions. And I discussed two ways to represent functions: representing functions as some integral transforms, and representing functions as flows, in terms of flows. If you can think of another way to represent functions, then we can come up with another class of machine learning models. I've tried to convince you that transforms are related to the random feature models and two-layer neural network models, and flows are related to the residual network models. As a matter of fact, if you discretize these continuous formulation, you would recover these guys. And the advantage of a continuous framework is that these continuous problems, you can cook up these continuous formula. Okay, formula is a continuous problem, so that they're not bad problems. Maybe they're not going to be convex, but they're not very far from being convex. For example, they don't have non-trivial critical points. Okay. And in terms of analysis, I advocated again a classical numerical analysis approach. Define the right approximation theory, direct and inverse approximation theorems, and then a priori and a posteriori error estimates, Monte Carlo-like error estimate. That's our goal. And at level approximation algorithm, even though there could be some bad news, like resonance, but because of these special features of the gradient descent dynamics, these are integral equations, not differential equations, not PDEs. So bad things happen very, very late. That saves us. So why things work? Well, so actually target functions can in many ways represent as expectations. And that's why things work in high dimension. And then these models that people use, there's some sort of a continuous background. These continuous background are sort of reasonably nice functionals, then even not convex, but they share features of convex functionals. And then the gradient flows are reasonably nice flows. And the dynamics helps to alleviate overfitting. Okay, basically because we're dealing with integral equations. And also that these machine learning models that people use in practice can be regarded as discretizations, numerical discretizations using particle method of some continuous problems. And they are naturally stable. I should, okay, so in numerical analysis, we emphasize design principles. So I think these should be design principles for machine learning models and algorithms. So why things don't work? Why things are still so subtle in practice? One of the subtlety is that these machine learning models can be unstable. So when I talk about many deep neural networks, I only spoke about residual neural networks. I didn't talk about fully connected deep neural networks. In fact, these are unstable in the sense that gradients grow exponentially fast as the number of layers increase. Okay, and there's this resonance. The resonance is not just affecting random feature model. Resonance is also a problem for neural networks. Okay, that's in the paper we're writing now. And there are other, GANs. For example, GANs is subtle because the landscape, the variational problem in the background is not a nice problem at the current formulation of GAN. And for residual recurrent neural networks, there are also other sources of instability. So these guys don't work because they have violated the design principle I proposed here. Okay, so there are many, many, many open questions. In particular, I want to mention that what we're aiming at is really analysis in high dimensional analysis. How do we analyze functions in high dimensions? How do we analyze PDEs in high dimensions? And we need a different viewpoint. And that's sort of the fundamental background that we really need to build in order to get a full mathematical understanding of machine learning. Okay, so that's what I want to say. Thank you very much for your attention. Sorry for going over time.
Oh, thank you. Thank you for the great talk.